Having talked about what goes on inside the sun, we now want to talk about the outside, the part that you actually see. Now, the sun's a gas, so it doesn't really have a sharp edge to it. And so when you look at the sun, it's really not fair to say it has a surface, but normally when people refer to the part of the sun they call the surface, what they are referring to is a layer that we call the photosphere. That's the region of the sun that's so bright and shining so much it overwhelms everything else. So when you look at a picture of the sun, that's what you're seeing is the photosphere. Surrounding the photosphere is a little layer right above it that is very thin and normally get washed out in most photographs. That's called the chromosphere. And then out beyond that is another layer that's even thinner, and that is the corona. No relation to the recent virus. Okay, so as I've said in class before, I mean, I call it silly calling it a surface since it's not really solid. So it's not really a layer. Rather a solid surface. It's a layer. It's a few hundred kilometers thick, and it's about 5,800 Kelvin temperature. We talked about the effect of it not being an actual surface. You can actually see a ways into it. You see the same distance into it, which is not quite as deep if you look at the edge, and that gives rise to the limb darkening that we saw. If you really zoom in on the photosphere, it looks grainy, and you sometimes see splotches on it. The splotches are called sunspots. In lab, we've already talked about the faculae, which are the bright region of the sun, and those little grains that appear in pictures of the sun are actually called granules. So granulation is all those granules. So the sunspots in this photograph, you can see a little bit of faculae over here, and then you have sunspots right there. And then you have the granules right here. The granules are actually caused by convection of the sun. Hot gas is rising in places where it's bright, and the cool gas is sinking in places where it is a little bit darker. So the hot gas rises a bit brighter, and so the granules are actually blobs of hot gas that are rising in the sun, and they are like roughly the size of the state of Texas. So you have imagine you have this blob of gas the size of Texas coming up and then sinking in a matter of about 5 or 10 minutes. So that's what a granule is. There's kind of a movie of a bunch of granules right there. And they last 5 or 10 minutes. The difference in hot and cool is only about 300 Kelvin. Skylab in the 1970s was studying the sun and using Doppler shift to see the surface of the sun rising and falling. That gave rise to what we call helioseismology. We can see regions of the sun rising and falling, and so that's due to shock waves passing inside the sun. It's kind of like sound waves passing through the sun. And so using that, we can probe the interior of the sun. And one of the things they notice is there's large regions of the sun that go up and down, things the size of the Earth, going up and down every hour. So it's kind of like granules, but bigger. So we call them supergranules. These sound waves shocking through the sun, bouncing around, are almost like a ringing bell. So the sun is ringing like a bell. And so, interestingly enough, there's a group of astronomers that study the interior of the sun by the shock waves going through it, and they call themselves the Global Oscillation Network Group, GONG for short. Measuring the shock waves going to the sun, that's where we figure out that the sun rotates differentially on the inside. In class, we talked about it differentiating on the outside, differential rotation. So the equator goes around faster than the poles. What we find is the entire inner part of the sun rotates at a different speed than the outer part of the sun. That shear in rotation turns out to be very important in determining how the sun behaves.